Alright, so let's move into the center. You do know, move into the center. I want y'all to look around the room because when you are stuck, you have a resource. It's called each other. Does anyone see anything that anyone did in class right now to get the equation of the original data? Or a model for the original data? Good. Then you're looking too quick because I literally see it already. I didn't say it was over there. I said I have already seen it in class. Shadija, no one's even over there. Nobody?
Oh, it's the one on the back. It's the only one different from that.
Nope, there's one that's more different than that.
It's that one right there.
That one.
Oh, what's that?
It's not this one.
Zen. His group.
What did the queens do?
Oh, the one.
They skipped a step that I would have written in there. Elizabeth, how did you go from that top equation to that bottom one? Please write in a different color up there. So like, how did you go from that top equation to that bottom equation? We didn't just magically write it, did we? What did you do? Okay, so you naturally saw it maybe. Miles, I hear you talking about it. What did you say? What did you say they did? Okay, but you all took a square root. Remember, we took our data and we took a square root, didn't we? That's why I had, Leah wrote this, right? That look familiar? Did it 3 or 4 minutes ago? Max? Guys, how do we go from here to here? It's already a square root. So, use inverse of the square root, right? What happens between the square root and the square? They cancel, and I'm left with this equation. Pretty sure we did that in class, didn't we? On Tuesday before we ended class? Not sure, didn't look at it since then, haven't even remotely thought about it. We had a test, I get it. But guys, so what can I do here to this equation? Thank you, same thing, guys. Ooh. Inverses still, right? Same exact thing. What's happening if I want what y hat is equal to? Right now I have the square root of y hat, so what's the inverse of a square? Root. Square. Whatever you do to one side of the equation, you gotta do to the other. Now please note and be careful about this. It's easy to not make the mistake over there with just one term. But here, please notice I didn't square the 0.32x and separately square the 0.42. I squared the entire side altogether. Please note that, because you cannot square individual pieces. So, for this group, it'd be 0.32x minus 0.42 squared. The predicted, and don't forget the context, the predicted, wow, that's terrible. Leah's going to make fun of me, but that's not cute and little. The predicted stopping distance is equal to this, where the x represents what? Guys, speed. Thank you. Didn't we look at how the stopping distance of a car is affected by the speed? Can someone move the camera really quickly? So this is a recap. This is not brand new information. I need us to pay attention to this. So as a small part of that recap, remember, we did linearize the data. Y'all can't see that. We linearized that data, but the whole idea is, if I were to go and graph, which I don't have it here. First off, how do I graph data when it's not actually on that graph?
Menu and scatter.
So remember, menu, right? That's the button that lets me do cool crap. From there, where do I go? Graph entry / edit. Trying to create a graph and a scatter plot. That's what it's called when you have individual data points like that. It's called a scatter plot. And so what did I want my x variable to be? Speed. So remember, hit the VAR, which you can't really see it right now, but it's above that number 9. It might help if you had a calculator in hand, looking at these buttons as I go back through them as a reminder. Okay.
I think it's the one like on our whiteboard.
Remember, you can hold, you can put your little cursor over that circular symbol, and it'll tell you if it's yours or not. Okay. So what was my independent variable? It was the speed. What was my dependent variable? Stopping distance, right? So we want to look at stopping distance, not necessarily linearize this time. Okay, I can't see much of that data. So menu, zoom data. Right, so we got that zoom data option. Now, I want y'all to remember this and pay attention to this detail. So we talked about this last time. If I try to take this line and I put it through there, we can clearly see, Elizabeth, can you hit the lights really quickly? You can see, is that data actually linear? You see how it's got a nice curve around that line? Because we talked about it. Why did we take a square root to linearize that data? Because this set of data follows what type of model? Started with a cube, a quadratic, a second degree, right? Not CU, with a cube, right? Quadratic, right? So we took a square root to linearize that data, and we realized, okay, first off, I need to point this out. How easy is it to figure out the equation of a parabola? When you got individual data points like that, do we have the vertex? No. Do we have the x-intercepts? So we haven't written an equation that way, have we? But I can move a line really easily. I need us to pay attention to that. I can't easily do a quadratic equation, but I can move a line. And so now I'm going to take that 0.32x and I'm going to square it. Tell me. Does that model those data points pretty well? Does it get pretty darn close to those data points? Yeah, right? That is a pretty good model. It's not perfect, but it's pretty darn good. Let's see if we check this one, the 0.32x minus 0.42. Okay? Notice that's close, but a little bit further off. So we would want to maybe go back and rethink our line, but that's pretty close. We got a 0.33x minus 0.42 over there. 0.33x. Ooh, that's pretty good. So maybe that'd be the model that I go with. Notice, is there only one correct answer here? The process is what matters. We linearize our data, fit a line to that data pretty well, and then we square it to get that equation. Now, what are your questions before we continue working specifically with this equation? Okay. So remember, once we get our model, we need to apply the operation we did to linearize that data, the square root of y hat, or square root of y, and then we can solve that equation. From here, oh, apparently I forgot to type in the next part of this. So we're going to hopefully finish up lesson 3, transforming nonlinear data and developing models today, which will then get us into a really important concept, lesson 4, which is understanding inverse functions. So notice, what have we been using, or what did we use to get the equation for the original model? What did we use to linearize the data? Inverses, right? But we've been using inverse operations. Well, inverse functions and inverse operations are very heavily related. However, they're not quite exactly the same thing. So what you've done with inverse operations, you need to hold on to this to solve for values of x. I think Malia's out the door. Can you let her know, or let her in? Huh? Well, so remember, what's a function? One input is mapping to one and only one output. An operation is just the square root, just the square, just the cube root, just the cube, just the logarithm, just the exponential. So the operation itself is just something you do to numbers, right? The function has those inputs and outputs. So fantastic question. You can get a piece of candy later for that question. So from there, and Malia, we'll get you to join the 10s, and Leah, you'll come back to the 10s, okay? In a second. So here's the proficiency scale to remember, right? Remember foundations, all of these foundations we've done before. We did talk about the idea of an index. What is the index of a radical again? The number in the crux? So what's the index for the square root? 2, right? What's the index for the 5th root of x to the 3rd? 5, right? So remember that index just tells us what root we're taking, okay? When we take a square root, don't forget, that means, hey, what was multiplied twice, or multiplied by itself to get that? When we take a 5th root, what was multiplied by itself 5 times to get that value? That's what we mean by those roots. We are finally, so we've already done determining if a function is one-to-one. We are now getting into this specific target of solving an equation for the input to determine the inverse function. And so when we talk about that, in general, how do we solve equations? What are we going to have to use? Say it louder. Inverses, right? I got a square root. What's the inverse of that? Well, it's square. It's not just a random 2, because that 2 could be a million things, right? A square is the inverse, and so we're using inverses to solve equations. Okay. So I already hinted at this today. I don't think we got a chance to write this down. So if you go back to your desk really quickly, I need you to look at lesson 3 at the beginning, and I need us to write down this note here. So this is the front side of lesson 3, I believe. Down at the bottom, I believe it is bolded there as well. So page 1 of lesson 3. Get a copy. All right, so we talked about this in the past. But I want, and I do distinctly remember Elizabeth bringing this up. I think it was Elizabeth. Someone else may have brought it up. But I want us to pay attention to this. Thinking about what we have done with quadratics in solving equations and what we did in lesson 2. Why is it more helpful to have linear data than nonlinear data when solving problems? There's 2 big things here. You don't remember what you said?
So you have a clean.
So first off, when you say clean, what do you mean by that? It looks better, right? And it's not just because we eventually get to the quadratic. It doesn't look super pretty, but how easy is it to write the equation of a quadratic if we don't have the vertex and we don't have the x-intercepts? Not super easy. How easy is it to just move the line around? It's pretty darn easy, right? It's easier to move a line than it is to write a quadratic equation. We can get a quadratic equation later. Guys, that's a big idea. This is bolded on the page for a reason. I see one person writing that down. Why do we want to have linearized data? Because it's what? Because it's what? Easy to graph or fit a, what kind of equation? A line to those data points. Sorry, Kennedy, remind me that I printed it out for you. Malia, you don't have this either, though, do you? Oh, no, you have this. Okay, cool. So, once again, why is it more helpful to have linear data? 1, because it is just easy to graph a line through linear data. It is hard to get a curve. Say again? It's bolded on page 1 at the bottom. Technically the front. See bolded down there at the bottom? Yeah, yep. It is easy to fit a line to linear data. It is hard to get nonlinear. Okay? Another point that I would bring up is this, and this is what Elizabeth mentioned, I think. I could be lying to y'all completely. what's going to be different about my number of solutions here versus my number of solutions here? What's going to be different about my number of solutions here versus my number of solutions here? Say again. One solution here and two solutions here. But more than likely, when we're talking about stopping distance and speed, how many solutions do we really want? One. We don't want guesswork. We don't want two. We typically just want how many solutions in the real world? One. So that's a part of it as well. We're going to talk more about that when it comes to a one-to-one function later. But big idea that we should have written at the bottom there is it's easy to fit a line to linear data. It is not easy to fit a curve to nonlinear data, or at least to get the equation. Maybe that's what I should make a note of. It's easier to get the equation of a line than it is of a nonlinear function. Don't forget on page 1 there's lots of instructions on how to graph scatter plots, things like that. You also have groups for a reason. And so we should have a note here. This is page 2, task 2 questions. This second bigger section right here, just as a reminder, what operation did we end up selecting that linearized the data best? What made that data linear? The square root. And how did we know, because this is what we should have written down, how did we know that the square root linearized the data best? Okay, so once we did it, yes, it made a straight line, but why did it make sense that it made a straight line? Say again, Jade?
Because it was quadratic.
Because we realized it was quadratic. I know I heard someone say that looked exponential earlier, and when you only look at half of a parabola can look exponential. However, what did we look at to realize it was actually quadratic? We looked at the table. We looked at the what? It's a 3-letter thing. We usually abbreviate it. Say again? Guys, we looked at the rate of change. And it was messy, but it was a linear additive rate of change. Think about what type of function it probably is and use that to help you figure out what will linearize the data. Okay, square root is the inverse of a quadratic. We get our equation from that. And I'm bringing all this back up because you're going to need to apply this in the next 2 tasks. Based on what we did a second ago, I'm actually going to pick this. It just looked like once we squared both sides. So y hat was equal to 0.32x minus 33x, that's what it was. It was really strong. Okay. Using the explanation above, write the linear model. So what was the linear model with the operation applied? That was the square root of y hat equals 0.33x minus 0.42. You can use your equation if you want. I literally have.
Okay, she got it on the outside, the prediction thing, and you got it on the inside. So which one is right?
To be honest,
It don't matter.
it doesn't, well, it kind of does, but with this equation, I'm not sweating it a ton, because this is not really the equation we want. This was to help us get this, right? Because it's more the predicted stopping distance, right? We took the square root of y. I'm not going to sweat that detail. The bigger thing is once you get to this model, then we need to use the hat there. Okay?
I'll do the same thing, just plug in, sorry,
Say that one more time.
I'll do the same thing, just plug in the same.
Yeah, remember I made that recommendation at the end. I would go back and put my variables in the context in there. It makes things way easier, and it will make things way easier a little bit later as well. So if you want to make that note, I would make the note that Mr. Kinney, recommends putting the variables back in as in context at the end here. It helps a whole lot to have the variables in context in that equation. Alright, our recap's almost done. We continue working with this though. So, this is the last thing we did on Tuesday. It's what we just did. What can I do to this equation to get a model for the original data set? So here's my model for linearized. And so maybe make that note to yourself. So model for linearized data. Right, that's this equation. What can I do to that to get the model for the original data set? I need inverses, I need squared, right? For when I say original data set, make a note to yourself that we want the predicted function. We want what y hat is equal to. And I wrote it this way because you pick which one you want. But for original data set, I want my predicted output to equal something. So what do I do to both sides? Square it. There we go. Whoops. It's got to actually have the square. So when we get to the model for the original data set, what do I need on its own? Y hat. Don't forget, it's predicted y. And after that, I do recommend going back and putting the context. Stopping distance, predicted stopping distance equals 0.33 times speed minus 0.42 squared. Elizabeth, can you hit the lights without moving? Otherwise, I'll come over. There we go. Just trying to make that easier to read for y'all. About to continue. Make notes that you need to make. Ask the questions you need to ask. And Miles, don't forget your candy. Unless you don't want it. And then I'll take it. Chocolates. Sugary things that are not chocolates. I got it. For the most part. If you want it, I got it. I feel like druggies were saying it like that. That was really creepy. I'm so sorry. So 0.33 times speed minus 0.42. Because remember, what I did is I put that variable speed in the place of x, because that's the context for x. Right? I'm predicting how long it takes the car to stop based on the speed. Okay. Say again, sir. This is a form of statistics? Yes. This is not, so there's like half a day to maybe a day in statistics where you look at nonlinear data like this. The vast majority of what we look at is linearized data. It's not very heavily tested on the AP exam, but this is statistics. So like when I say that like that, it's not much of AP statistics, but it's very heavily statistics because what statistics is one, messy, two, real world data that we're analyzing, right? We're analyzing real world data to help us understand or get to inverse functions, okay? Now, at this point, we are moving to the task 3 questions, okay? So I'm going to look at the context with you, and then I want you to go to your vertical surfaces. I want you to write what the independent, dependent variables are in this task. Think through how we're going to linearize the data, all that stuff. So, and I'll explain a little bit of this in a second, because it blew my mind when I realized why this works. So, motorboats, jet skis, the whole nine, right? When you're going out on the water, you still want to know how fast you're moving. At least I do when I go out on a boat. So, motorboats have speedometers or tachometers that determine the speed in knots, which are nautical miles per hour, I think is the right term. So in knots of the boat by measuring the hundreds of revolutions per minute of the motor. The RPMs are converted to display the approximate speed in knots of the boat. And I will say that boat speedometers, not as accurate as car speedometers, but they're pretty close. And so we're going to try to linearize the data that we get there. So what I want you to keep in mind, we're trying to figure out like what independent dependent is. the boat measures this thing, and based on this, they get the what? The knots, right? So the boat measures the revolutions per minute of the motor, and based on that, it's spitting out a speed in knots, okay? So what I want you to do is I want you to take your sheet with you. I'll give you time to write notes down, so just one of you needs it per group. And I want you to look at your knots. I want you to try to first identify what's independent, what's dependent. That should take just a minute or two, and then let's try to linearize that data. Once you think you've linearized that data, by the way, I need everyone using the calculator. So y'all talk as a group, but I need you to all make sure that you agree on what linearizes the data. Once you linearize the data, go to 3.3 and try to fit a model to that linearized data. What are your questions about these instructions? Yes, Landon. That's a great question. So the real complete answer is it can be either. Let's transform the dependent variable. So then, what? You think the knots are dependent? Then yes. So yes, when you start transform your dependent variable. Great question. Thank you. Let's get up to vertical surfaces. Let's go. And Landon, if you want to get a piece of candy, you can. Excellent questions. Y'all know where to get the candy from? Yeah. The box right here. That's my stash. So remember, let's talk with each other. Talking makes learning more fun. But let's try something else because we can clearly see, right? Leave this on there really quickly. I want to show that to the class really quick. All right, guys, if I can get y'all to move into the center really quickly. Move into the center. I just need you for like 30 seconds to 60 seconds. Please move in. All right. Class capture. And then, all right, so what did most of us think might linearize this data to start? The square root, right? And I'm going to look at the table in just a second, but I want y'all to look at this, right? So this is a graph of once we took a square root. When you look at it like this, does that look perfectly linear? Not at all, right? I see it kind of curving and then curving. And so, man, that does not look linear to me. Sometimes it's hard to see. Mary, you with me?
Yeah.
Okay, you sure?
I was not out.
Okay. Sometimes it's hard to see from a table. But does this kind of remind anybody of anything we might have studied? Similar to any kind of function?
Quadratic.
You sound like you're just guessing at this point. You ever see an exponential that has a curve like that? Where it's going down like this and up like that? Maybe a polynomial? Any guesses at what type of polynomial maybe? Maybe a cubic? So what should we try if we think that's cubic looking? Okay? So let's look at, so I'm not confirming or denying. I'm going to stop presenter here. So Miles, I'm going to put your calculator up. If I can find you. Why are you hiding like that? All right. So I need y'all to pay attention and think through your calculators. So, oh, you already did it. Okay, can you go up here really quickly? So click up, hit it, clear it out. So hit delete really quickly for me. Yeah, delete the whole thing, okay? Well, that's fine for later. So please be in that box and hit equals for me, okay? So we should see this when we hit equals. We should all be at this point. Kelly and Elizabeth, do I need to come over and get y'all to here? We good? We're good? Okay. So we should be at this point. So what am I going to do if I want a cube root? So I just want to make sure we know how to type this cube root in. Okay, control and then what? The little hat, the arrow. So it's called a caret mathematically. So if you hit control and then the caret, you see how there's a little root symbol above it? Okay? So So notice what's going to go here for the index. 3. If we want a cube root, put a 3 there. Go inside to your radicand. This is why we need to know that language. What are we going to do to put our knots in there? Hit VAR for variable, and then just hit knots. And then hit enter. Okay. And so I want to look at a couple of things here to make sense out of this. Because we do want to recognize, to go from 1.35 to 1.84, what is that about?
About 0.5.
0.5, yeah. 0.5, 1.8 to 2.35, 0.5. Now 2.35 to 2.57 is not the same. 0.22, 23, 22, and then here is 0.22. Now, does that look constant additive to you?
Yes.
Well, yeah. But it's close.
It's close.
It's messy but close.
With dealing with such small numbers, I will say that's not super close, but do this for me really quickly, Miles. Go to 3.3, the next slide with the graph on it. Oh, we added that in there. Okay. Can you click on this point right here for me, Miles?
Which one?
Just any of the red points. And then hit delete. And then now zoom data to these data points. It was trying to zoom to both of those sets of data points. That's why it looks like that. So, it doesn't look linear here, does it? But what about if we look here? Is it somewhat scattered around that?
Yeah.
Remember, the real world's what? Messy. When you start driving and you're accelerating, it takes a second to start accelerating, doesn't it? Takes a boat, the same idea. So this early bit, that doesn't look very good, does it? But when we look at the rest, once we start speeding up, does it look pretty linear?
Yes.
And that's what we want to notice. Earlier with that square root, not only did it not look good here, it also didn't look linear there, but here we at least have a section of linear set of data. So one, what type of function would model the original set of data? We took a cube root, so the original data would be cubic, okay? This somewhat linearizes it. If I'm personally doing this, I'm also skipping, I'm kind of ignoring these points here because they don't really fit the linear pattern. And guess what? Is that okay? The real world's messy. Sometimes you have to ignore certain data points because they don't fit the pattern. And so that's something we're going to talk about. So, I want y'all to each have your own equation. We have a cube root that's linearizing our data. Now, fit a model to this and start working through questions. So, I should probably number these questions, but I need you to move through the rest of the questions on task 3 page, okay? So I need us to get done with that hopefully in the next 6 minutes, 7 minutes. Work with each other, but I want to get through the last task today before tomorrow. So help each other out, work with each other. That's it.
Wait, what?
Okay.
Yeah, we did square and then
Where did it work?
didn't work because it's a cubic function.
Thank you.
Because
Alright. So, if I can get y'all to move into the center so we can talk about this and apply this. We've got a lot of good ideas. But I want to firm these ideas up, and I need the person who has done the least talking, the least writing, I need them to be the one driving everything this time. So that means you have to talk through things. Now, I want to talk through a couple of small things to learn from and do better on. And I'm going to give you some time to take some notes. It helps if I have a purple marker so you can see my notes. Excuse me. Alright. There's my purple. By the way, I heard an allegation that I've run out of expos. I have not run out of expos. They're right here. People trying to spread rumors about me, and I don't appreciate it. Elizabeth. So, Actually, I have 2 more boxes beyond that.
Well, then put them out.
All right, we're here. So really quickly, I need us to be careful. Right here, I see the note cube root of knots. But right here, what do we have? That's the square root. Be careful and make sure you put your index in there, okay? So it's the cube root, and like y'all worked it right from there, but I also want to point out, I need y'all to look, right? When I look over here, I'm going to come back to some of these things in a second, but I want us to be careful. Like, when I'm looking here, I see a claim for an equation, all right? But how do we get to this point? How did we get to the predicted f of x equals this? Right, but like, so show me your scatter plot real quick. Go to 4 current. Okay? Did you use someone else's? This one? Huh, I don't know where it went. So it's not there right now, but here's the thing I'll point out. Everyone used what to model that data? A what?
Graph.
Linear, a line, right? Linear function. We don't have a linear function up here. What I need you to do is I need you to pay attention. Okay, take the time to say y hat or f of x hat. One of those two equals 0.16 x plus 0.68. Now, to get to here though, right? Not just to get to here, but what did we do to be able to get a linear function? What do we do to the dependent variable? As you've all been doing this, we took a, say it louder, did we take a square root this time?
Cube root.
So we took a cube root, didn't we? So notice I started with my linear model. I have shown my inverse operation applied to the dependent variable. Now what can I do from here to get my model for the original data set? If you are skipping steps, then you're going to lose this because you're going to lose the big idea. Like, what can I do to go from here up to this equation? Inverses, right? Mary, what's the inverse of a cube root? Then how did y'all get to here? It's up there if you look at it.
That's clearly not my kid right there.
So how did you get that?
Davis wrote that.
Davis, where you at? How'd you get there?
I just get someone else.
You just stole somebody else's. If you're stealing somebody else's, is that learning? Can you look at someone else's and say, oh, that makes sense now? Sure. Can you look at someone else's and say, like, I still don't understand, and go over there and ask them? Sure. Stealing someone else's work's not going to help you learn. So I need y'all paying attention to this. First off, when I'm looking at our graphs, we didn't have our linearized model anywhere. The linearized model for that group was this. But what am I going to do to that? And then we put the cube root, because that's how we linearize the data. What am I going to do to this equation to get y hat? Davis, any guesses? Okay, so we got to stop stealing people's answers, right? Kyron, tell me, what are we going to do? Okay, guys, y'all are breaking my heart. Listen, okay. You are in small groups of 3 for a reason. Because 3 heads is better than 1 head. If you are standing there and someone does a thing and it doesn't make sense to you, then what do you need to do? Ask a question, right? And this is again why I said, if you're the one writing everything, you need to give up that marker. Because I need you to talk through these things. I've got about 6 or 7 students who are grabbing that marker first every time. If you're that person, and you know if you're that person, give it up to somebody else in your group so that you have to talk about it. Give it up to the person who needs to be writing and needs to be talking so that you can learn and grow the most. Because once again, if you're the student who's doing and it's making sense while you do it, the way you learn it better is by explaining it to somebody else. If you're the person who's struggling to figure it out, the way you learn better is by asking questions and making sense out of it. So if you're the one writing, what are you going to have to do? You're going to have to ask a question. Learning is the priority. I know that we're not used to focusing on learning. We're used to focusing on a procedure that a teacher tells us to do, and then we just keep doing over and over again. But Kyron, tell me this. What is happening to y hat? What's that symbol thing there?
Which one?
The symbol thing happening to the y hat. If I cover up the y hat, what's that thing?
We got the variable.
No, I covered up the variable. What's happening to that variable? It's the only thing left that we see.
Crossing it out, right?
No. What is this symbol right here?
Square root.
You're close. I'm going to come back to you in a second. Crystalline, can you help him out?
Cube root.
Why do we know it's a cube root?
So you got a 3.
Because you got a 3 for the index, right? A square root doesn't have anything there. If it was this, what root is that going to be, Kyron?
Quartic.
You can also just say a 4th root. So a quartic root or a 4th root, right? Because there's that. Davis, what root would that be? 5th root, thank you. Okay, Taylor, what's this root? 7th root, okay? So let me ask you this, all right? When I look over here, Hope, what's the inverse of a cube root? Okay. What's the inverse of a square root? Let's go back to that. The inverse of a square root was a square, right? So what's going to be the inverse of a cube root? A cube. Yep. Bella, what's going to be the inverse of a 4th root? So remember, the inverse of a square root is a square. The inverse of a cube root is a cube. The inverse of a 4th root is going to be a quartic or a power of... Okay. Bella, what's going to be the inverse of the 5th root? Power of 5, okay. Davis, what's going to be the inverse of a 7th root? Power of... Guys, that's it. The roots are the inverse of the powers. So Mary, if I have the 8th root, what's going to be the inverse of that?
Power of 8.
Power of 8, yeah. 100%. So, we did the cube root of the left-hand side. What else do I still need to do? I need to do it to the other side. Remember, that's going to cancel out. It's the inverse of the cube root. And whatever I do to... Whoops, I should have done it down here. And whatever I do to one side, I have to do to the... And notice, that's canceled, so what am I left with on the left-hand side? Y hat, f of x hat. What am I left with on the right-hand side? The 0.16x plus 0.68 cubed. That's how they got that. It matters that we understand the process and the why. Don't steal other people's work. Go and ask them. That means you actually have to talk about the math. And you know what happens when you talk about the math? You learn it better. Guys, the things that you care about, what do you do about them all? What do you do with them all the time? Miles, tell me something you care about. What's something you really enjoy? There's nothing in life you enjoy? You make me so sad. Bella, what's something you enjoy? Say again. Seeing your family? Do you talk with your family? Do you talk about your family to other people? Really?
Like in a good way and a bad way?
Both?
Yes.
Okay. I literally was assuming that you would jump to volleyball, but that was just me.
No volleyball.
Do you talk about volleyball some?
Yes.
Because guess what you do with the things you care about? You talk about them. Thank you. And when you talk about those things, what does it help you to do? It helps you to learn them and understand them and think about them. You got to talk about it. I know math is one of those things like, but Mr. Kenny, I don't love math. Cool. It's okay. When you talk about it, though, you're going to learn it better. Whether you're crushing it usually or whether you're struggling with it usually, when you talk about it, you learn it better. So, we have our equations. What I need you to do is to go through the notes there, and I need you to make notes to your future forgetful self about this. because we got one more task where we're going to be applying the inverses, and it's going to help us learn about a new type of function. So make your notes about what you can. There's a couple of questions I want to address before we end class today, but I need you to actually write some stuff down. That if you went back and looked at the rate of change, you know what kind of rate of change this function would have actually had? Any guesses? A quadratic additive, right? This was a cubic shape. And so if you went back and looked at the rate of change, it's not going to be perfect because the real world's messy, but it would have had a quadratic additive rate of change. When we looked at the graph, we saw that the graph had a cubic shape to it. And so we took a cube root and we went from there. So why do other operations not work? Well, because it was a cubic function. The only thing that undoes a cubic is a cube root. We needed the inverse operation. Okay, we needed the inverse operation. Mary, you got all that?
Yep.
Okay. Trying to think of anything else. I don't think so. The last thing I do want to make a note of with the last couple of minutes in class. So, one, we have got to get to the last task tomorrow for sure. So that's task 4. But before we get out of here, okay, using these equations, yeah, we got plenty of time. We have y hat. Yeah, that's plenty of time to do what I need to do.
You was what did.
I got ears. So remember, this was our model, but y and x don't represent the real world. What was y? It was the knots, right? And so we've got our cubic function. And so Elizabeth asked a great question here. We put knots in the place of y, the dependent variable, right? So how do I read this? The predicted knots. Make sure you have that prediction in there, because that curve is not perfectly hitting the data points. It is a predicted set of knots equals 0.13. What is x? Hey guys, for real, we got a minute and a half. You got plenty of time to pack right here. What is x? RPMs plus 1.16 cubed. That has real world context. The predicted knots is equal to 0.13 times whatever the RPMs are plus 1.16 cubed. We got to finish the last part of this lesson. Yes, you can hole punch it. We got to finish the last part of this lesson ASAP tomorrow. We will start there, and then we will move into lesson 4 to at least start getting into the inverse function side of it. So all we've done is inverse operations still. We got to figure out what is an inverse function. Looking forward to seeing y'all tomorrow.
Mr. Penny,
Say again?
Penny help.
Yeah, sorry. That's it took me a second to realize it too.
Hey, what's my question?
Yeah. Do you want a piece of chocolate? Hold up. It's close to being good enough. I'll let it go.